AP Stats, it's the last day of content. I know we've got a lot to review, but this is the last bit of new information. And it's just section 3.3 in the book. It's transforming data to achieve linearity. So here's a graph of showing the length and weight of Atlantic Ocean rockfish. And the first question is linear model appropriate? Answer, of course, is no. No, because the pattern appears curved. Is curved. But the other thing you'd notice is if you actually did, I mean, you could do the linear regression on the calculator and you could find an equation of a line that would fit the data, and it would go through the data. So it'd probably be something like about like this, maybe something about right there, something like that with a little bit below and a little bit above, and you get the data. If you looked at the and you get the line. If you look at the regression, the residuals plot, then what we'd see for these low values. So I'm putting length here, and then I'm putting residuals. How far off the line is each point? Then what you'd see for low length values, you'd see a positive residual. Remember, if you're above, you've got a positive residual because it's actual minus the predicted that gives you your residual. So, I don't know exactly how much it is. Maybe it's about 150 or something like that above the line at this point. So maybe this is, we're not going to be too much over that. So I'll say 150 right there. What the heck? And so it would start off, we could mark these and start off positive, and then it'd be a little less positive, and then it's pretty much right on the line, and then it starts going a little bit below the line. So these points represent the residuals for each point, working them out. But you'd see I hope you're seeing what I'm talking about, that there would be like this pattern where you'd have an underestimate because your residual is positive in the beginning, and then you'd have an overestimate, and so your residual will be negative, and then eventually again it would become positive again. Remember what we said about the residual plot is that we want this to be random scatter. We want this to not show a relationship, and so that would be another indication that the linear model is not appropriate. And so, I mean, it's enough to look at this original and say it's curved, don't use a line. But this is just another way you might see it, is they might show you a residual plot and you say, oh yeah, look at this pattern in the residuals. So no, another reason is that there is a pattern in the residuals. And we want our line to just have noise around it to show that our model is fitting the data in a way that doesn't show a relationship that's sitting there that we're ignoring. So how do we deal with this? And one thing that's interesting about this section is that this section has a lot of work on the brain, a lot of calculator stuff. There we go. This section has a lot of calculator things that you need to do. And remember, we're not using the calculator on the AP test. So what does that mean? That means we're going to have to be able to make decisions and choices, but a lot of the skills that we might practice in this chapter, we don't need to practice. I'm listening for the applause right there. So what will happen is, if you have a set of data, then we can try to linearize the curved association. What happens is they take all the data values and they do some sort of transformation on the data values. Like one thing they could do is they could cube, this is the first one, they cube the length values. This kind of makes sense because length is one-dimensional, like in centimeters, and weight is like talking about the whole mass of the object, and so it's talking about a three-dimensional aspect to it. And so there's some logic in just cubing the length values. And look what happens when they cube these length values. They end and then look at the data with the weights unchanged. You notice that now a line is a really good fit for the data. And there's no pattern that we can see beyond this linear association. So now we've got a very good model here. When we compare weight to length cubed, we see a good linear pattern. And so here's the equation. Here's the information for the equation. Remember how to read this is that, and we're just going to use these variables here. So weight is my y. So weight hat, the predicted weight is the constant 4.066 plus, and then the coefficient is 0.0146. I'm trying to keep some of those significant digits there for accuracy, times the x variable, which is length cubed. Blow this up. There we go. That's better. So now we've got a model, and notice how it's a linear structure to it. It's just that the variable is not a linear variable. It's the length cubed. But this is still using linear regression. It's doing linear regression with transformed data values. So, and then it says, what would predict the weight when the length is 36? So I'll plug in 36. I'm going to do this in a second. I'm going to do it 2 at once. And so I'm going to show you another one. Another thing they could have done was they could have just done it the other way. They could have cube rooted the weight, and that way getting them to be the same dimensions. Remember, this is and this is still length down here. So length now is unchanged. And so what do they have for an equation then? So it's now my y variable is this thing. So that is the cube root of weight is my variable hat. My predicted cube root of weight is the constant negative 0.022 plus the coefficient for length, which is 0.2466 times the length. There's no exact number of digits. Remember, no calculator needed, so you're not going to be taken off for a certain number of digits or something. So this is another way we could write it. Now, just to compare these two, I'm going to plug 36 into each one of these models because that was the other part of it, and see what I get. So I'm going to pause for a moment and do that. Okay, I've plugged the numbers in. I plugged 36 into this equation, and I got a weight hat of 685.2. Ooh, we should have units there. That's grams. And notice how when I look at the original data, if you put in 36, which is about there, getting 680 seems in the ballpark. You know, I can't say exactly. And actually, it does a better job than the line because it looks like it's a little bit higher than the line. It's pretty hard to tell though. The other one is I plugged 36 into this equation. So when I plugged 36 in, I could work out this side, and I ended up with this. And then I just had to cube both sides. You know, just cube this, and I got the weight hat being 694 grams, 694.5 grams. Slightly different, but you can see they're basically the same. And you can see that our R-squareds were really, really good using these models, which is some evidence that it's an improved model. Now, the other thing you can use is logs. And so here's the log example. So this is using base 10 logarithms. And you notice now the R-squared is actually even better if we log both variables. So it's the same idea. This is the equation here. But now they've actually transformed both variables. The y variable now is log of weight. So I'm going to write that. Log of weight equals, and then my coefficients, blow it up a little bit, make it a little easier to read. Actually, it's more to make it easier to write. Negative 1.899 times the coefficient for the x variable, 3.049 times, and my x variable is log of length. I need a hat on that, but otherwise there's my equation. Perfectly reasonable equation. It's just both variables have been transformed. Remember, you're not going to have to pick a transformation yourself in the sense that you're not just going to be given a curved data set and then you have to find the transformation because you don't have a calculator. So that takes that part out of it. You would just look at the situation and say, well, this is what the model is, and it's a really good model because it's super linear and the R-squared is great. So now, state the equation when length equals 36. So again, you'd plug in 36. And this is the one little bit of logs you need to be able to deal with. It's going to be very small. Whoop, that should be a plus 3.049 times log of 36. So now I'm just going to work this out on my calculator. This is a fast one, so negative 1.899 plus 3.049, and I'm using the log button times the log of 36, and I'm using log because it's base 10. Remember, base 10 logs, you use that log button, and so I get 2.846. 2.846. Is that right? That's right. And that's log of weight hat. But I want to know what's the predicted weight itself. And so I need to solve for weight here. This is the one little bit of there we go. I'm just writing a better log here. Yeah, that's the one little bit of logs you need to be able to do is to solve an equation like this. That's it. And how do we do that? Well, remember, this is base 10. And so there's different ways different teachers have of showing that. I go with the angle method. So we use big 10s. And so we're going to do 10 to that. If these two are equal, then 10 to this equals 10 to that. And 10 to the log base 10 of weight hat is just weight hat. That's a property of logs. And weight hat equals, so I have to do 10 to that answer. 10 to the last number I had, and I'm getting a slightly bigger value, 701.7, which actually looks a little better to me in the original graph. You can go back and look at the original graph, and 36 it seemed like it was closer to the weight seemed like it should be a little bit bigger. So grams. Yeah. One other thing. No, that's it, actually. I'm sorry. I got distracted there for a moment. So that's how to, just check my time, pretty good. That's how to do that. And so now, so here's another example. And this is the original data right here, the original data. And now in this one, they just logged the y's, and that's it. But this time they used natural logs. So we want to make sure you can handle natural logs also. Tell you what, take a moment and write the equation. And then we want to predict the number of transistors in the year 2020 using that equation. Go ahead and do as much of that as you can, or all of it, and I'll show you the answer in just a moment. So pause the video right now, as in now, pause it, and try to answer this question. And I'm pausing too. Okay, I plugged in the year, I set up the equation. Natural log of transistor hat is, and then just use the coefficients, and that's the linear model. And then I had to plug in the year, but notice that the variable is years since 1970, and we want 2020. So you had to plug in 50, because that would be the year since 1970 for the year. When you work that out, you get this. And so now remember, we want to solve for t hat, and so now, when we use natural log, remember that's base E, that magic number E. So to solve for t hat, for transistor hat, we just have to use big E and do E to the on both sides because these things are equal. And so you get transistor hat equals, and E to the 24.9, which is 6.69 times 10 to the 10th. So that's 6.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9. Boy, I'm getting an answer here of 60 billion. 60 billion for my predicted number. Now keep in mind though, what we're doing though is we're doing a little bit of extrapolation. So we're ending up getting an answer that's way off the chart, because if this pattern continued and then kept going for that space in between, it would be shooting up really, really high. We'll talk a little bit more about this in a second, but I'm going to need to make a second little video. That's how to do the math in terms of making a prediction, in order how to read a line and make a prediction for the year 2020.